So you have in the syllabus, which is available in PeopleSoft, some kind of a brief description of the class. So half of the semester, maybe more than half of it will be, I will be covering some fundamental things and also giving you some base to understand different processes. Then once you get this base worked out with your projects, then we're going to go and do some more practical stuff that you will be asked to explain based on physics or chemistry that you hear from me during the first part of the course. What I'm hoping to get here is that you guys eventually get a good foundation in what is called electrochemical thin film growth, and you understand that there's no magic behind electrochemical deposition, which is commonly misguided principle when you go to industry. When I got my job after finishing postdoc in Brookhaven National Lab, I went to Seagate Research in Pittsburgh. It's the company that makes these hard drives. And so over there was some kind of a myth that, electrodeposition is like a hocus pocus thing, right? So you just do a little bit something, you add some weird stuff in the solution, and for some reason you're getting great stuff. And it's mainly portrayed by these old people who have no clue about the math, about physics, about chemistries, but they have a lot of experience. And so when you ask him, why this works, he really doesn't know how to tell you or explain to you from the point of fundamental science that is involved. But he just brushes it off and tells you, don't ask me this question, it does work because I tell you to do this way and that way. So part of the reason why I'm teaching this course the way it is that experience in industry which was actually pretty bad. It was pretty bad in a way that it took me a long time as a manager of the electrochemical fabrication group. I was in charge of every single electrochemistry process that is involved in a thin film heads fabrication. And a lot of these processes were actually licensed from IBM. And the bad part about this, when you sign the license agreement with some companies, that you cannot reverse engineer the process because that's forbidden. And so you have to always call them if something goes wrong, and they come and supposedly fix it. But in virtually 2 years, I got rid of every single license we had. We had 100% of our solutions, chemistries, alloys, everything worked out, with also everything implemented in production. And the people from IBM started to hate me because I was stealing their bread and butter. Because what IBM does today is just sells the licenses to their patents. And they find morons in industry who don't know anything about, but these guys come and say, if you do it this way, and this is a black box, you're gonna get this, don't ask the question, you pay that much every month, and you get what you want. And that works in some ways if you're not really interested in advancing yourself or making your company license independent, or if you have a lot of money to spend on licenses, which are not cheap, by the way. Most selling patents today, or the largest revenue that IBM ever generated from any intellectual property, is the permalloy electrodeposition bath and a paddle cell, which is used to grow thin films in most of the magnetic recording industry. Those two patents generated more IP money by being licensed to every single manufacturer than anything else IBM have done in history. So, for that, in IBM obviously you have some smart engineers, but you also have a lot of people who are not capable of understanding what's going on, and for that reason they have a good business. The best thing I want to do if I'm in a consulting business is to keep my customers in the dark, and they have to call me every single time they have a problem. And I do that, by the way, it's a good money. here you are to learn something from me. So next time you end up in industry, being paid well to solve the problems, knowing what I have in mind to talk about this semester will help you greatly in deciphering a lot of myths and legends about electrochemical thin film growth. And so to start with that, we're going to discuss first the cell thermodynamics. So what is the cell? Cell is basically, when we think about electrodeposition, is basically a closed system which represents counter electrode, reverse reference electrode, and working electrode solution, and it assumes that volume of the cell is constant, temperature is constant, and pressure is constant. In 99% of the time when you do any kind of electrodeposition, this applies. And in the 1% of the situations when this doesn't apply, is some kind of an exquisite or really exotic examples which are not that important in general to be covered in class. Come by quickly, right? So now everybody here about yes.
So is it 16 answer?
Yes. About first law of the thermodynamics. What's the first law of the thermodynamics?
Energy cannot be created or cannot be destroyed.
All right. How about applied to the closed system? Any change in the internal energy of the system is equal to the difference between the heat flow in and out of the system minus the work the system does. You see that there is a difference how I E, Q, and W work versus internal energy, which is U capital. Why is that? Well, you probably know, but I'm just going to mention here from the thermodynamic point of view, is that we have intensive and extensive thermodynamic quantities. When something depends on the mass, the number of moles, we have a capital F, like internal energy, like entropy, like enthalpy, like free energy, etc. When something is not dependent on the quantity, molar quantity in the system, like heat, work, and so on, we have a small f, okay? Let's make this distinction right away so you guys know what I'm talking about, right? There's a reason why this is like the way it is. That's the first law of thermodynamics. All right, what's the second law? What does it mean? Second law of thermodynamics. Anybody has any kind of idea from the thermodynamic classes you took a long time ago or maybe a short time ago? If I bring the heat in the system, whether I bring or remove the heat of the system, if the system is at a constant temperature, what will it really change is order in the system. If I bring the heat, disorder becomes higher. If I remove the heat, order becomes higher, right? You probably heard about entropical death of the universe. Means the universe will be expanding, eventually. At one point, everything will be so far from each other that will be entropical death. All right, so this is the second law of the thermodynamics. If you do combine first and second, what you really get, so this and that, you get Q is equal to, not Q, sorry, U, W, changing internal energy, is to delta S T minus W. All right. W is still not very well explained here because W is the work. Now, work in our case, I'm gonna put here so you understand what we're talking about, is the work that could be done by the system, and it's mechanical work, which is P times delta V. And I'm going to keep this for a second, although it's not really important at the moment. And the electrical work, which is equal to N times F times E. This is electrical work. Electrical work means that you move the charge, and the charge is given by this product here, N, which is the number of electrons per whatever unit species. This part is constant because this is the charge per molar quantity. And since we are really talking about in terms of the molar quantities, this needs to be quantified as something totally, right? So if you have that many, 1 mole, it will give you this type of N times F. And E is the electric field. So if you move the charge in the electric field, you do the work. That's very important. If you move the mass in a gravitational field, you still do the work. If you move the magnet in a magnetic field, you do the work. Now, for our purpose here that we're discussing electrochemical cell, there's no magnetic field. The gravitational field is more or less constant everywhere, so you don't do any work against the field, etc. And so what is only really relevant are those two terms, although this one will drop off soon. Okay. All right. So now, from the thermodynamics, you remember that entropy, delta H, is equal to delta U minus T delta S, or S delta S dt, right? Actually, no, sorry, it's not. I'm going too fast. It's basically the difference between its sum of the change in internal energy and mechanical work, V delta V, okay? That's enthalpy. Now, we also have other fundamental relation which explains the total energy of the system, and it's especially important when we talk about chemical energy when we do a reaction. So it's called Gibbs free energy. Gibbs free energy is defined as delta G is equal to delta H minus, and then we have this specific term which is basically given as T delta S. Now, if you combine this equation, and this equation, what you're going to get is that delta G is equal to, I'm going to just make it short, is minus W plus P delta V. Now that minus W means minus NF E minus P delta V plus P delta V. So this comes from 1 plus 2 plus 3, right? And so in the end, what you end up with is that change in the free Gibbs energy of the system, such as our electrochemical cell, is equal to negative work done against the electric field. It's an important relation, which I'm going to recall a few more times in the next few minutes. But I'm going to keep it here for you instead of erasing the board. If we have to erase the board, I will probably get back to this in a few seconds, okay? So this is important because what we're going to now talk about is a little bit, I'm going to call conceptually, it's really not that difficult for people who are chemical engineers, who have dealt with different rates, who know what transition state theory is, who can handle the chemical kinetics. but even for them it might become a little bit hushy-pushy, okay? The reason I do this is that you need to understand the fundamental meaning of every constant in the Butler-Warner equation for electrochemical kinetics, because tomorrow you might be able, just by looking at the data, to understand a lot more than what most of the people that don't have this kind of a background do, and it gives you advantage from all that. Also, there is a lot of books written in electrochemistry. Virtually none of them is good, and for the reasons that everybody can write a book today, so picking the right book is actually becoming a difficult thing. The second thing is that to write a good book, you have to understand what you write about. And today people are just basically writing things that they don't understand. So when you go out there and look at electrochemical books or book about electrochemistry and so on, be careful what you read, because a lot of books are not actually explaining this well. That's why we're going to go through electrochemical kinetics in more detail than usual. All right, so this is good. All right. So now I'm going to give you just an idea what we're talking about. We're talking about electrodeposition. Right, so that means this is our electrode. This is our solution, right? In this electrode solution, we're going to call the state of our metal, because let's say I'm going to simplify to a point where you're just going to talk and understand today's lecture in terms of metal deposition, although there's a lot of other electrodeposition things, right? But let's stick to simple things and we're going to complicate later on. So here, the metal is in null state, meaning it's just a bulk phase. That's a copper electrode, for example. Here we have a different form or different phase of that same element, and it's basically N plus, and that could be, for example, copper 2 plus solution, right? There's an interface between bulk phase, solid electrode, and solution, which, among many other things, has this type of ions, right? For the purpose of the derivation, I'm going to call this reduced form R naught, and I'm going to call this oxidized form OH and plus, and concentration of these two forms of the same element. This one is obviously soluble in electrolyte, like copper ion, for example, surrounded with a lot of water molecules, sulfate ions, etc. This is just a solid copper, right? I'm not going to use M naught and M plus, I'm going to use R and O, because I think probably 50% of the books use this kind of notation. Now, also, you have to keep in mind that this R and O notation, meaning reduced versus oxidized form, can also apply to some electrochemical reactions which do not involve metal deposition, but actually involve some kind of electrochemical oxidation of one ion to some higher state, or electrochemical reduction of some ion to lower state, etc. So basically, all these could be covered by electrochemical kinetics we talk about today. Now, in terms of the further introducing some terminology, I'm going to call this oxidized form. And by the way, these brackets means concentration, but anyway, I'm going to keep them in this. Going into reduced form, and I'm going to call this reaction, which is obviously a reduction reaction, because oxidized form receives the electrons and becomes a reduced form. I'm going to call this cathodic reaction. And then anodic reaction basically reduced form, losing some electrons, becoming oxidized. Right? So this is just basically terminology of what I'm going to operate with in the next minutes. All right. So if you get this, now the important thing is to go a little bit in excursion about rate theory, reaction kinetics, and stuff like this. Now, how many of you have any idea about that? It's not a difficult concept, but it's important for you to focus on what I'm talking about because this is not complicated. Yet, because of the notation and because of the math and because of many other things which are gaps in your education and knowledge, it looks ugly right away and most of the people don't want to see it. Actually, it's super simple if somebody explains you this properly, right? And so that's what we're going to go about. Now, let's consider chemical reaction, and this comes from the rate theory or transition state theory. I'm going to say that here I have oxidized form, and then at room temperature, whatever, let's say some conditions which are normal, viscous pressure and temperature, this oxidized form needs to go into reduced form, or wants to go to reduced form. In the energy diagram, which is the free energy G, and this here is called reaction coordinate, and I'll explain you what is this. It's some kind of distance, but for you at the moment you don't have to really worry about this because it's not important. But if I have this oxidized form, and this oxidized form wants to go to reduced form. In terms of the free energy, obviously the spontaneous process happens when the delta G of the process is less than 0. What that really means is the free energy of the products is less than free energy of the reactants. So for that reason, if I do react, I go to the lower energy state. That lower energy state makes me want to go and lower my energy because everything in the nature occurs according to minimization energy principle. So if I'm standing here, I prefer actually to be sitting. This guy obviously, if there's an opportunity to go to a lower energy state, it will happen, right? According to transition state theory, this will happen only if along this reaction coordinate, it surmounts the activation energy of the transition state, or basically activation energy. In this transition state here, what we really have is not fully reactive thing, but this guy is in some kind of a relation with, it's some kind of a conformation where the molecule has approached the electrode maybe just to get into the tunneling distance for electrons and things like this. The ionic atmosphere around is just reconformed, so it allows this kind of a tunneling to be truthful, etc. So this is the transition state. Nature requires that you have more energy than what you do have at this level to be able to kind of react. So basically, reaction never goes like this. Very few reactions are barrierless, by the way. There are some barrierless reaction, which means this is actually not existent, or it's very small. Or, as compared to the term RT or KT, RT is for the molar and KT is atomic quantity. What it really means, the thermal fluctuations are lower in terms of energy than what is required to reach this state. That's typical. Now, if the thermal fluctuations are really high, it means if I crank up the temperature of the system and I bring the average energy of the system very close to this, then the reaction might become very airless. But for this electrodeposition, which is room temperature process, we consider this type of diagram to be okay. Now keep in mind, what I'm trying to tell you is that I still don't talk about electrodeposition. This is purely chemical reaction. For example, let me give you an idea. This could be that your metal ion reacts with hydrogen. And let's say this metal ion could be, let's say, zinc, whatever. And it's reduced simply to metal plus 2H plus, right? And let's say in this case N is equal to. That could be purely chemical reaction. So we are not talking even about electrodeposition at the moment. It's not electric field, there's nothing else, it's just like a chemical reaction, right? So I'm going to introduce some terminology which we're going to come back and reuse. All right, so having said that, let me introduce some quantities which are essentially important here. If you think from this point here to this point here, the reaction that goes this way, which means from the reduced state to oxidized state, we call this anodic reaction. The energy required to surmount this barrier, actually, this reaction to happen, is called delta G. I'm going to call this hash O, right? I'm going to give this subscript A. So, not every particle in the system has this energy, but the ones that have enough energy to go over this barrier will eventually come here. It's probably not spontaneous process because delta G in this case is bigger than 0, but let's just focus on terminology, right? In this case here, this is delta G hash not cathodic, because this is a cathodic reaction. Oxidized species goes into reduced state, right? Now, this cathodic and anodic notation still doesn't have a real meaning, but I don't want to introduce this later on, so I'm just giving you an idea that basically we still talk about some kind of oxidation or reduction, and whatever leads to oxidation is anodic reaction, and whatever leads to reduction is cathodic reaction, okay? So just keep that in mind as a terminology introduction. Now, in chemical kinetics, we have rate laws, right? What we're going to assume is that according to chemical kinetics of this reaction, that the rate, and I'm going to put this as R, of the anodic reaction, which in units is in moles per second, so it's not a flux, it's a rate, moles per second, is proportional to some rate constant Ka times concentration of the R. No. That's a first order reaction kinetics. That's the assumption. And it works really well for what we're going to discuss. At the same time, rate of the cathodic reaction, C, is equal to Kc times oxidation, concentration of the oxidized species. And this Ka and Kc are the rate constants. And obviously, R naught and O and plus are concentrations. Right? Okay, so no potential, nothing has happened. I'm not turning the knob, I'm not applying potential to the electrode. This is what happens just spontaneously due to the chemical affinity. As I mentioned here, for example, some metal being reduced by hydrogen, or there's other explanations and so on. this chemical story, I'm now going to add electro part. So we talk about electrochemical reaction. Electrochemical reaction is not the one that happens due to the chemical affinity, but it's the one that is enforced by the electric field of the system and happens due to the presence of the electric field across this interface. That's electrochemical reaction. So now, in order to change this diagram, I have to put the term that will tell me how this delta G that I'm changing is a function of the applied potential across this electrochemical interface, right? Keep in mind that this extra delta G that I'm going to put to change this little bit balance due to the now presence of the electric field in the system is equal to minus NFE. So if I add some delta G here, okay, now I'm going to have a new level, and the difference here will be minus NF, some potential that I'm applying across the interface, right? Okay. So my new level of the energy of my reactant and plus will be here due to the presence of the electric field across the interface. Now I'm going to just change a little bit this initial thing so I can draw correctly. So this is the delta G. This is the delta G. Alright. So now, when I introduce this field, obviously I'm shifting the starting energy state of my reactant. And so now I have a new situation. Obviously, the energy state of my product doesn't change. It's the same all phase. But the energy state of my starting phase is altered by this term here, minus NFE, where N is the oxidation state, the number of electrons transferred in the reaction that we discussed here, right? And so, what is the difference now between the maximum here, which is the transition state energy? I'm going to say that it's a function of this term here, for which I alter the energy state of my reactants, but the presumption here is that this difference here is basically given by beta minus beta NFE. Obviously, it's not equal to this because this beta term here is less equal to 1 and bigger than or equal to 0. What I'm really implying here to tell you is that the height of the barrier is dependent on the altered potential across the interface, but it's not exactly the same. It's proportional to this beta, where the beta has the boundaries between 1 and 0. If it's 1, then this increase in the height of the barrier is equal to exactly this term here. If it's 0, then the height of the barrier doesn't depend at all on the altered initial state of the reactant. Okay, so you kind of get the idea. So it's a trick that we use in logic. All right, keep in mind this. All right, now it's easy. Let's do some algebra together, because this is what everybody fails to explain in the books, at least properly, to the students. And the worst part is that because it's so ugly, or everybody who writes the book thinks it's super easy, nobody really understands, and we have generations of the students that don't have a clue how to handle this very simple thing. Okay? Now let's explain what is really cool here. Going back and defining this constant Kc, this is the rate constant. And I'm not going to go into rate theory and transition state theory, this is a little too much of the work, but I'm going to say that Ka as well as Kc are of the form where the initial part here is some kind of a, we call this transmission coefficients, and I'll explain what it is. Then there's a kt divided by Planck's constant, and then e to the minus delta g over RT. This delta g here is the free energy of the activated complex, and this K is a Boltzmann constant, temperature, Planck's constant, and so on. So what we really have is that this rate constant has the form, which is something that you heard in Arrhenius theory, and this is a little bit modernized Arrhenius theory from the point of view that we know a little bit more about statistical mechanics and typical terms and so on. But the bottom line is this: that this term here, and I'm going to call it K naught, whether it's A or C, doesn't matter. It has the units in frequency, and you can check yourself. And this term here is an exponential term that is basically similar to what you know from Arrhenius theory, where this delta G is like activation energy, but it's actually energy of the activated, free energy of the activated complex, right? Okay. So we can define now Ka to be equal to K naught A e to the minus. Now, I'm going to talk to you right now, first in terms of just a black curve, the initial situation, right? And I'm going to say that this here, for the anodic process, which is this thing here, delta GA over RT, and Kc is equal K naught C times e to the minus delta G naught C. That's this thing here, right? So we don't consider yet application of the potential across the interface, and we're not talking about electrochemical reaction, but just the chemical stuff, right? So we can define these two constants this way, right? Okay. Now, let's do a little bit more at this point before I waste this board. Okay. I'm asking you, let's calculate the new situation when we apply the field across the interface and see how now our values of delta G hash. So now the new delta G hash is this one here. We'll call this delta G hash C. And the new delta G anodic here, hash anodic, is the one that is a result of the application of this potential across the interface. So let's figure it out. What's the new situation? Obviously, for without potential, we can see those are clearly identified, but now since we shifted the initial energy state with the application of the potential across this interface of this reactant, situation looks a little bit different. All right. So let's see what the Ka is equal to. Now I'm going to call this Ka now the same way as I call this Ka, but instead of here having this not term, it will drop off because we have now potential involved. I don't want to have hundreds of different notations, so you just understand what I'm talking about. So the Ka is the K naught A, which is this frequency term, e to the minus delta G hash A, right, over RT. And Kc is equal to K naught C e to the minus delta G hash C over RT. Okay, So this applies to the red situation here. Right? Okay. Now, I'm going to move to a new board, but you guys keep this in front of you because it's important. And I'm gonna redraw just for the sake, actually I don't have to redraw because I can actually continue here. So then by the time I develop these equations, we're gonna go to a new board so you can follow easier. Okay, so let's define delta G hash A. That's the activation energy right now of the complex energy, the activated complex when we have applied this term here, right? Or field across the interface. Okay, what happens? Well, this is our delta hash A, and it's equal to delta GA hash naught. And then we have to add this form, which is basically minus this, right? So this is basically equal to delta G hash A, right? Anodic. And then plus this height here, which is some delta G, which is equal to minus beta N. So minus beta N F E. Very easy, right? You just read the diagram. Now delta G hash C is equal to, the situation here is a little bit different, but not so difficult. If you think about this term here is actually this term plus this term minus this term, right? If you look at the logic, it's very simple. This term minus this term, and then I add this term, right? So this part here is delta GC naught minus this, right? So we can say delta G naught hash C minus this term here is the minus, minus is plus, so it's plus NFE, and then plus this term here, which is the minus beta NFE, right? If you want to do a little bit of the arithmetic, this is delta G C hash naught, and then if you do the math here, this is plus 1 minus beta NFE, okay? So now we have the activation energies when we add the field across the interface, which basically brings in our whole discussion electrochemical reaction, right? From chemical to electrochemical, basically as you can see, the activation energy is just modified for anodic process due to this term here, which kind of increases a little bit the activation barrier. And here is a little bit more complicated because we are shifting the energy state of the product or the reaction, and then we have to do a little bit more math, but it's relatively simple. Are we clear with this? Because if you're clear with this, then you have no problem with anything else besides math. Okay? How we do with the time?
7, right? Right now 6 to
6:20. 6:20.
20. Beautiful. All right. Can I move now and bring this up? Okay. Going back to the rate equations, as I said, the anodic rate is equal to K anodic, which we said it's a K naught anodic, E to the minus G star anodic over RT, and rate of the cathodic reaction is K naught C E to the minus delta G hash C over RT. Okay. Now, I'm going to expand right now these exponential terms by supplying these expressions in each of these, right? So, implicates from one end to here, but I'm going to get that anodic rate of an anodic reaction is equal to K naught A e to the minus. What do I have here is delta G dash naught A minus beta and Fe over RT, and rate of the cathodic reaction with the presence of the field across the interface is K naught C e to the minus, and now here we have delta GC hash naught plus 1 minus beta and Fe. All right, over RT. Okay. This is beautiful because it helps us further simplifying the situation. If I expand these exponents in a way that if I have this minus, I'm going to just move into, get rid of the brackets and put this into product. So it's going to look like this. RA, which is the rate of the anodic reaction, is equal to K naught A e to the minus delta G hash naught A over RT times E, this minus, and this minus gives you plus. There's going to be beta and F over RT. All right? Times E. The rate of the cathodic reaction is K naught C e to the minus delta G hash naught C over RT times E. This minus coming here, it's basically E to the minus 1 minus beta NF E over RT. Okay? I didn't do anything special besides expanding this into a product of exponentials and so on. That's a Mickey Mouse math. You shouldn't have no problem. But here's the cool thing. This part here and this part here are something that we know where it comes from. Those are just this chemical affinity. Remember, those are the black curves in our diagram, right? So these are actually our chemical rate constants, which we defined, if you remember, I discussed that. So this here is the Ka, and this here is the Kc. So finally I can write the rate of the anodic reaction to be equal to Ka capital E to beta NF over RE times E, which is the potential across the interface, and RC is equal to capital Kc E to the minus 1 or minus beta and F over RT times E. Okay. So, obviously what is really important is that now when we have potential across the interface, when we are driving reaction with application of potential, the rate is dependent on this potential, obviously, and also pre-exponential factor is related to these chemical constants, which in essence contain the free energy of the activated complex without any field apply, right? So the correction for the field like is in these exponential terms here. Everybody clear with that? All right. Beautiful. Now, what we're going to do now, we're going to derive a Nernst equation, which is the equation that defines the equilibrium potential as a function of the concentration of the products and reactants in solution from the kinetics. When do we have equilibrium? Right, let's consider for a brief moment the interface, and this is anodic, and this is cathodic reaction. When do we have equilibrium? When both rates are equal, right? So what the really equilibrium mean is that R anodic is equal to R cathodic, right? Because, keep in mind, in electrochemistry, equilibrium is not static, it's dynamic. Things are happening, but the rates, the net rates in equilibrium is zero. That's what is really important for you to appreciate, right? Okay, so what really happens when you have, let's say, copper in equilibrium with copper ion, is you have a really high intensity of the exchange between copper bulk and copper ions coming out and coming in, right? But the net rate is zero. That's equilibrium. Okay. If you look at these two equations, what that really equilibrium means is that the Ka e to the beta and F over RT. E now, I'm going to call this E equilibrium, because this happens when we are at equilibrium potential. That's the idea here, right? It's not any potential. At particular potential, I bring these two rates, so I modify this, if you remember, and I bring these two rates to be equal, because I can modify the whole diagram by adding one or another potential, bringing down, bringing up, delta G is equal to zero. Basically, that's the idea whole of the process, right? And so that means that this is equal to Kc e to the minus 1 minus beta and F E equilibrium potential over RT. Okay. If I do the log of both sides, I'm going to get log ln Ka plus beta and F over RT times E equilibrium is equal to ln Kc minus 1 minus beta and F over RT times E equilibrium. Okay. What I really want to do is then keep the ln Kc as a positive, so this moves here, it's going to be like this. ln Kc here minus ln Ka, the K brings into the logarithm is going to be ln of Kc or Ka. Okay? And I really don't like this term here, so I'm going to multiply everything by RT over NF, so I'm going to have here RT over NF. Okay? And then what I have here is on the other side is basically when this whole thing moves here, what I'm going to have is plus beta E equilibrium, and then plus 1 minus beta E E equilibrium, right? It's equal to, right? So this is what we get. Now obviously this guy and this guy are canceling each other. On the end what we really have is, I almost forgot something about. Now, just bear with me. I made a mistake here, not including concentration. Right? So the rate here tells you that the rate, first of all, the reaction kinetics is equal to RA is equal to concentration of the reduced species Ka, right? And Rc is equal to concentration of the oxidized species times Kc, right? So when we do this kind of thing, what we really are missing is his reduced species concentration And so what we really, when we do logarithm here, we are missing because this ln kc should be here plus ln oxidized species. And here you should have extra ln of the reduced species, right? Anyway, then without too much problems, we can keep this plus ln, and then what happens is that, you know, if you move this to the other, you know, this is equal to ln of oxidized species over reduced species concentration, RT over NA, and minus, and it's actually like this, plus is equal to E equilibrium. We can solve this. I made it a little bit messy because I forgot to introduce the concentrations, but it's really not a big problem. And all right, this equation here seems like it tells us that equilibrium potential at which we have the rates of the anodic and cathodic reaction equal has a term which is the concentration dependent and a term that is not concentration dependent. Now, the classical definition of the Nernst equation tells you that the equilibrium potential is equal to the equilibrium potential at standard conditions plus RT over NF ln, and then you have oxidized species concentration divided by reduced species concentration. Okay? That's standard notation. So obviously this term here, which is the concentration independent, if I put 1 for concentration of oxidized and reduced species, which is standard conditions by definition, this drops off, right? Because ln of 1 is 0. So I end up with the equilibrium potential being equal to this term here, which I'm going to call equilibrium potential at standard condition, and this is plus RT and F ln oxidized species divided by reduced species concentration is equal to E equilibrium. This is basically the same thing that we know from before. This is the dynamic definition, which uses a different definition of the to get to this point, but this is a Nernst equation coming from the kinetics, right? What's the time right now?
6:30.
6:30.
All right, good. Are we clear about this? Any questions? So the only thing I made a mistake, I didn't include the concentrations, but shouldn't be a problem, right? Any questions? Any question, chemistry guy?
Not yet.
You have seen this before, right? In
Yeah,
chemistry.
I've seen
All right.
that before.
Okay, so now we're going to determine or derive a bottle warmer expression, which is the basic equation for the electrochemical kinetics. Now to do that, I need to sacrifice this writing here. Is that okay with you guys? I need to erase this.
Yeah.
All right. I should have a helper coming and raising this board while I'm taking a break. Natalie, you will do this? Don't worry, don't worry, don't worry. Have a seat here. It's not beautiful because these erasers are kind of but hopefully you guys see clearly, alright? Okay. Now one thing that we do in electrochemistry, instead of measuring net rate, what we do measure is the current. That's how the instrumentation works. We measure the current. The net rate between cathodic or anodic reaction is some kind of a, whether it's an anodic higher rate versus cathodic, and so you measure anodic, which is positive, or cathodic, which is negative current. You always measure some current as a function of the potential applied across the interface, right? So, what I'm going to say is that I'm going to have rate of anodic minus rate of cathodic reaction being equal delta R. But at the same time, I'm going to have a current that is the manifestation of the different rates, because current zero means the rates are equal, is equal to, if this is some kind of moles per second, then if I multiply this by the number of electrons transferred across the interface times the Faraday's constant, which is corresponding to the charge of the mole, and then delta R, I'm going to get the current, right? And this is equal to F times, now difference of the rates, anodic rate is the K anodic per concentration of the reduced species, E to the beta, and F over R T times E minus cathodic rate is the Kc, concentration of the oxidized species, E to the minus 1 minus beta, and F over RT times E. Right? Okay. Now let's say this E is some arbitrary potential, but we want to have a different rate. So we either drive the reaction in anodic or cathodic direction. And what I'm going to do is a little trick and say that I'm going to introduce the number or notation in a way that this is a overpotential, and it's equal E minus E equilibrium. So whatever potential I apply across the interface minus the potential at which the interface is in equilibrium gives us this term which we call lower potential of eta. Okay? What that really means that this E, which is an arbitrary applied potential, is equal to eta plus E equilibrium. Right? Everybody clear with that? Okay. So my current that I'm supposed to register is equal to NF times, and I'm going to right now replace E with this thing here, so it's going to look like Ka R E to the minus beta and F over RT, eta plus E equilibrium, minus Kc, concentration of oxidized species, E to the minus, actually here it's not minus, here it's right? Minus 1 minus beta and F R T. Okay? Times eta plus E equilibrium. That's the expression for the current that I'm supposed to see. All right, what's next? Well, let's look this here in the brackets thing, so everybody's okay with this. If I look this thing here, and if I remind you how the first expression looks like here. And first expression is given here, which is the one that I'm going to reuse for equilibrium potential. Just bear in mind here, RT over NF, logarithm Kc over Ka, RT over NF logarithm with the ratio between the concentration is equal E equilibrium. So I can put all these things back, right? So let's do this. So it's going to look like this. Current is equal to times K-A-R E to the beta NF over RT times beta, okay, times E to the beta NF over RT times this E equilibrium, which is going to be in the brackets, which is going to be RT over NF ln Kc over Ka plus RT over NF ln oxidized species concentration divided by reduced species concentration. And then I'm coming here minus Kc, concentration of oxidized species, times E to the minus 1 minus beta over RT and F times beta times E minus 1 minus beta over RT and F here times, and again I'm using all these things, okay? Which is basically RT over NF ln Kc over Ka, then plus RT over NF ln oxidized species concentration over reduced species concentration, right, in the bracket, okay? It's become cumbersome expression, but it's a very simple one. The reason I'm doing this so you understand some definitions and also you understand some formulations. People usually don't do this kind of derivations in the book. They think it's too simple, but it's not. It's important for you to guys to appreciate what we are actually doing here. Okay. So this term here, obviously, nothing to really change about. I'm gonna keep it the way I want it, because we have this over potential term, it's fine. But what we really want to look here, look at this. NF over RT multiplies RT over NF here, RT over NF here. So this drops. Okay? What I really have now is beta multiplying this term, and when the beta multiply in front of the logarithm, if it goes under the logarithm, and this is exponential of the logarithm, I can, instead of writing all these, all these things, so this stays the same. But instead of writing this e to the logarithm, beta logarithm this, I can write basically Kc over Ka on power beta. I hope you understand what I'm doing, because this is still math. And then times, it's going to be again beta, and logarithm drops, so it's basically oxidized species over reduced species on power beta, okay? Now what I really now want you to pay attention here is that here I have Ka, concentration of the reduced species, times E to beta NF over RT over potential. And this multiplies this one here. Now, look at this. Ka here is in the denominator, which means basically Ka is the 1 minus beta. And this Ka here, you end up with Ka1 or minus beta, right? Then you have Kc to the power beta. Then you have R, and this is R on the minus beta, so it's basically R concentration to the power 1 minus beta. And then you have oxygenated species to the power of beta. And then you have this term here, which is e to the minus, e to the beta and F potential over RT. Okay? Now minus, and we have here Kc, concentration of the oxygenated species, multiplying this term here, e to the minus 1 minus beta and F over RT times eta lower potential, and then the same things apply here. You have NF over RT, multiplying RT over NF here, RT over NF here, so this conveniently drops. And so what you have really here is that you have minus 1 over beta, and when it goes to Kc over Ka in front of, within the logarithm, what you end up with is the Kc over Ka on minus 1 minus plus beta, right? And then the same thing here, which is times oxygenated species concentration divided by reduced species concentration on power minus 1 plus beta. And the cool thing here, if you look, these two multiplying Kc multiplying here minus 1, and the 1 plus minus 1, what you end up with the Kc is just basically a minus. It's just a beta, and oxygenated species is just a beta. And you can see that this is equal to these two terms. And what we also left here is a Ka, which is Ka, and then it's minus 1. And this is Ka, so it's basically simple. Well, minus of this is 1 minus beta, and R is simply minus of that is 1 minus beta. Okay. You can see that the term that multiplies this exponential form and these terms here that multiply this exponential form are equal. So they could go out of the brackets. When they go out of the brackets, what we're going to have, we're going to erase this just to finish this part of the lecture. We're going to have a very simple solution, and we're going to have nice form of the equation, which tells us that the current, which is equal to the, which raises as a function of the consequence of different rates, another direction, is basically that current is equal to NF multiplying Ka 1 minus beta, Kc on power beta, R on power 1 minus beta, oxidized species on power beta, multiplying again e to the beta and f over RT times over potential eta, minus e to the minus 1 minus beta and f over RT over potential eta. Alright? This thing can come here together with this one, and basically we're going to define new term called exchange current is equal to NF Ka 1 minus beta Kc over beta R power 1 minus beta oxidized species this plus power beta. And so the whole new Butler-Warmer expression is now given as A current is equal to I naught, which is exchange current multiplying the difference in these two exponentials, which is e to the beta and f over RT times eta, which is our potential, minus e to the minus 1 minus beta and f over RT eta, right? This is Butler-Warmer equation that describes electrochemical kinetics. What is really important right now, and all this math is done here, so you can see that this term here, I naught, called exchange current. Or, if we introduce, instead of talking about current, talk about current density, we divide this by the area. So it could be J, which is J is equal I over area. And then J naught is the exchange current density, I naught over area. It's it's important for you to appreciate that this p-exponential factor here in the expression is a function of the concentrations of your species. Now, for the case of deposition, R by default could be considered 1 because this is above phase of development, right? However, these constants and the oxidized species, which are copper, for example, ions, play an important role in the value of the exchange current density. Which means, if I have a higher concentration of copper ions in the solution, I will have a higher value of the exchange current or exchange current density. By itself, I'm going to have more higher activity or higher current registered as a function of the rover potential because this 3 exponential factor is larger. That's essentially really important. If you want to get high kinetics, and we're going to talk about it during electric deposition, it's essentially important that you have high concentration of the ions. First, to offset the transport limitations, we're going to talk about this later. But the second is to improve the value of this 3 exponential factor, which is the function of the concentration of the ions in the solution on the power beta. What is the power beta? Another question. This term here, beta, is a symmetric factor. We talked about it. It tells you how much or how more or less, depending on the introduced potential across the field, free energy of the total reaction changes, but how much of that value actually changes the height of the activation barrier. Okay? So it's a fraction thing between 1 and 0. But what is important is that some people call this NF is equal alpha anodic, which is anodic coefficient, and this term here, 1 minus beta times N, is alpha cathodic, right? What it really means is that alpha anodic is a function of, this is N beta, sorry, of the beta, which is between 0 and 1, but N is the number of electrons or oxidation state of your ions, or number of electrons that are transferred across the interface per every atom you deposit. So, beta between 0 and 1, alpha depending on N could be between 0 and 2, 0 and 3, depending on whether you have 3 plus ions like chromium 3 plus deposition, etc., etc. So, same thing here, right? Okay. So you do understand the difference between anodic and cathodic coefficients and symmetry factor beta. It's a fundamental difference. Okay. Also, very important thing, if you look this expression, it might remind you of one known have you ever heard about hyperbolic functions? You don't know what hyperbolic functions are? Right. In the case that you have beta 0.5, that means that 1 minus beta and beta are the same. That means that alpha anodic and alpha cathodic are the same. In that case, this whole expression looks like hyperbolic sines. Hyperbolic sine function is equal, sine hyperbolic is equal to e to the x minus e to the minus x over 2. So, in a case this alpha A is equal alpha C, then your current is equal to 2 sine hyperbolic 2I naught sine hyperbolic, and then of this term here, which is the beta NF over R d beta, which you can come up with the expression. Okay? That's only special case when you can use hyperbolic sine form of the van der Waals expression. But this is the true one that you find in the books. In some instances, as I say, you don't see N and beta, but you see just alpha A and alpha C, right? Some people even use alpha A and alpha C, like alpha A being equal beta and alpha C equal 1 minus beta, where N still this factor here. There's a different notation in different books. As long as you know what it means, that's why you go through this derivation, then you shouldn't have any problem with that. But this is the essential equation of the electrochemical kinetics. Everything starts from here. And again, derivation is not that complicated once you adopt certain notation and you start to deal with this from the fundamental point of view. It takes a little bit of the writing, but I think it's a good exercise for you, so we will come back on the next class to this equation and start simplifying it and explaining the effects and so on, how this affects the kinetics. Do you have any questions?
Not right now.
All right. These derivations, I've done it because you have recording, you can go back and remind yourself. You have in plenty of books, but not necessarily they're clearly done, unfortunately. So, if you find a good book, good for you. I suggest you look the lecture at home and you derive yourself, and that gets into your background and you have no problem anymore, right? Other than that, I don't think your guys gonna have any problem. Okay, that's it for today. Okay.